you don't know me. So I'm Yuna. I'm working for Drew Shindel. I'm postdoc here. And I've been here for 1 year. And okay, now I want to introduce our speaker, Jing Li. She recently graduated from Columbia, and she will stay at GISS as a postdoc. And today she will talk about one of her outstanding work she done during her PhD.
Hey, thanks for coming. So basically this is part of my defense, but for some of you didn't have a chance to show up on my defense, this is a good chance to make up. I'll talk about a optimal fitting approach to improve the aerosol size, parameterization, and optical properties in the GCM. So I'll first introduce the GCM aerosol parameterization. That's only the radiation part because I'm using the radiation model, and the mass density are from the chemical transport model. Then I will present a assessment of the aerosol optical depth as from exponent and single spectral video simulation by comparing with satellite data and AERONET. Then next, I will show some results of a sensitivity study on the direct radiative forcing to perturbations in these aerosol properties. Then I will introduce this optimal fitting methodology, and that's partly based on the results of the sensitivity study. Then I'll present the results and some implications in future work. So in the aerosol model, we have 6 species, and their mass density are from the chemical transport model from ModelE. And then in the radiation model, we specify their size, their mean parameters, and the hygroscopicity parameterization. And these are the 6 species here, and that's how their mass are specified. And this is their dry size. And we have several size bins for that. Then, so sulfate, organic sea-salt, and nitrate are hygroscopic. So next.
So this is not Suzanne's aerosol.
No, yeah, this is Coke's. So this one has no microphysics. It's like
so this is the previous generation, basically, of the.
Yeah, like the 2008. Yeah, but I'm planning to use Suzanne's tool, to running this method later. So after their mass are specified here, then this tau is optical depth, so this mass is transferred into tau by this relationship, and this Q extinction is the extinction efficiency, and we also have scattering efficiency to calculate the scattering part, and this is the specific density of the aerosol itself, and this is the effective radius. And we only have external mixing here for now. So this shows how this model aerosol optical depth field compared with ModelE to satellites, and this is AERONET. So in general, they have similar patterns here, also here, but probably we have a little bit overestimations over the best regions, and also some underestimations, especially over the absorbing aerosol regimes like South America here and South Africa here, and also East Asia. And overall, our global average is lower than ModelE and MISR. And this one only has land data, so it's significantly higher, but we basically get the same results. Then this is Angstrom exponent. So it shows like the size of the aerosols. While ModelE and MISR also has some differences, and this is AERONET, but GCM is kind of lower compared with all of these 3. Even though these two don't agree on the absolute value, but to be much lower than the satellite and the AERONET. So that suggests that our aerosol sizes may be too large. Then next, this is single scattering albedo, shows the absorption of the aerosols. So this is GCM, this is GCM sampled AERONET station because we don't have absorption from satellite, so I only have AERONET here to compare. I kind of sampled GCM at these AERONET stations. Clearly, our single scattering albedo is biased high compared with this one. So that means we also don't have enough absorption. Then that's the like the distribution or relative values. So here I also compare the seasonality, and this shows the correlation between the mean seasonal cycles of AOD, Angstrom exponent, single scattering albedo between the GCM and AERONET. And this is the correlation coefficient, so it goes from -1 to 1. So this correlation seems pretty high for tau. It's generally about 0.5 overall. And then for these two, we have a much lower correlation. The global mean number even go to negative, and also for these. So we have problems between also in the seasonal variations in Angstrom exponent and single scattering albedo.
So all these optical properties are moist for equilibrium. Are they for dry? I mean.
They are for not dry. Some are hygroscopic.
So you swell them up.
Yeah.
Good.
So from the comparisons, we can conclude that our aerosol global distribution or spatial variability seems to be fine compared with satellite and AERONET, but AOD is kind of underestimated, except over the Sahara we have a little bit overestimate. Then we have a significantly low bias in the Angstrom exponent and high bias in single scattering albedo. So that suggests that we have two major problems. One is the aerosol sizes may be too large, and then also we have insufficient absorption. Then I did some sensitivity study to see how the perturbations in these three affect the radiative forcing, because that's the thing we care the most. The idea is that we perturb these three parameters by AERONET precision. For AOD and single scattering albedo, we perturb them by AERONET precision, and for the Angstrom, we are like scaling the size, the dry size of the aerosols by 20%. And then we'll see how the forcing changed due to these perturbations. And this table shows the results. So this is how they are changed or perturbed in these. I also included the symmetry parameter here, but that shows the least change, so it's not very significant factor. Then this is how they are perturbed, and this is how the forcing, direct forcing changes. And originally we have -3.5 watts per meter square direct forcing, and the anthropogenic part is -0.24. And this is how it changed due to perturbations in those parameters. So we can see the greatest change happens when we kind of increase the Angstrom exponent, which corresponds to a decrease in aerosol size. The next single scattering albedo also has a significant influence on the forcing here. And the third one is optical depth. And also we need to note that these numbers are even larger than the Angstrom anthropogenic forcing itself. So that means the forcing can be very sensitive to perturbations in those parameters. So it's kind of it's a highly uncertain parameter here, and that suggests we need to do something to adjust the aerosol size in the model, and also may need to adjust the absorption part. Then, so this table here shows how the sizes are specified in different models. This is from the AERONET project, and these are the are different models. This one is the GISS model, and this is the aerosol species. So here we can see that the GISS aerosol size are generally larger compared with our other models, and also some models have bimodal or some multimodal distribution for some species, especially dust and sea salts, but and also for some other like organic and black carbon, but we only have one mode for these aerosol species. Then, as mentioned, our aerosol size may be too large. The next, I will introduce a method to adjust the size of the aerosols. So we take this AERONET station as an example. These triangles are AERONET observations for this station, and this is GCM result, the solid black line. And this is for different wavelengths from 340 to 870. And these three are absorption optical depth. Then this comparison shows that we have, so our tau at this longer wavelength seems okay compared with AERONET, but it's very low at the shorter wavelength. So that suggests a shallower slope of tau. So that corresponds to a larger aerosol size used in the model. Then based on this comparison, we define a cost function, which is the sum of the mean square error between model and AERONET. So this is the mean square error, and with the sum means this thing for all these wavelengths, but is kind of normalized by the variance of that wavelength, because the magnitude or order of magnitude for different wavelengths are different. So this, so we sum up this normalized mean square error and try to minimize this cost function by solving for the effective radius, and also adjust the fraction of absorbing and non-absorbing aerosols. Then finally, we want to, we are able to make it like this. So this red are fitted GCM result after adjusting the size and the fraction of absorbing and non-absorbing aerosols. So this shallower slope has been corrected once we kind of decrease the aerosol size. So that's the main idea of this optimal fitting method. So the treatment of this effective radius is like discretized because this extinction coefficient is nonlinearly related to effective radius. Then in the model, we use a lookup table of this value computed at discrete effective radius. So here we use a similar approach. In solving for the effective radius, we use discrete values of the radius that's based on its original value. Currently, we haven't adjusted that size because it already have the 7 size bins and allow some flexibility here. So that's the idea of adjusting the size and also the fraction of absorbing and non-absorbing aerosols. And then this figure shows results for some aerosol types. For this is yes, kind of small, but this is dust, and this is biomass burning, and this is rural aerosols. Then these three species are have the best results. Here is how this is the original result, and this is how it's changed after the feeding. So most of the low values are corrected, and the correlation is also improved. For the other two aerosol types, that's urban maritime aerosols, the fitting also improved the results a little bit, but not as good as the previous three. There are still some kind of outliers here. And also the absorption optical depth is still pretty correlated. So that we still have some other space to improve, and the sources may come from the mass density itself or some relative humidity field, which affects the hygroscopic growth of the aerosols and then its size. So the maps here shows the distribution of the fitted sizes and the fraction of absorbing and scattering aerosols. So mostly we need to decrease the size from organic carbon from 0.3 to 0.14 microns, and then also decrease black carbon, nitrate, and this one's sea salt. Overall, it's decreased from 1 to 0.84. Then we can see some places need an increase, some need a decrease. It's more like a bimodal distribution here. Then the fraction of absorbing aerosols need to be increased by 2. That means we need to approximately double the amount of absorbing aerosols. And this is the rest is like 1.52. That means our total aerosol optical depth is also underestimated by approximately this factor here. Then this I made an initial attempt to use those fitted sizes and parameter fraction into the GCM. And this shows the optimized aerosol field, and this is top surface forcing, and this is absorption, atmospheric absorption. This is the original, and this is their differences. So from here we can see the greatest changes in the Angstrom exponent, because previously our values are biased much lower compared with satellite. Now there's an overall increase in Angstrom exponent, and its global mean number increased to 0.74, which is close to satellite data. And also the absorption seems to be increased too, with single scattering albedo value become lower than the original aerosol field. Now this is 0.92, this is 0.95. It's a little bit lower, and as we are using AERONET data, which only has land observations, so most of the ocean areas are not really adjusted. So the global mean number is now very different. But from the maps, we can see many of the land places has significantly greater absorption here. So the forcing change, also we can see that the atmospheric absorption here seems to be increased relative to the original value, we have the most increase over East Asia, like this one here, and also India, and South America and South Africa. That's most of the absorbing aerosol regions, and now their results have been greatly improved. But these are still some initial results because our data, AERONET does not have global coverage, and there are also some issues in maybe the chemical transport part or relative humidity that are not considered here. So, so in conclusion, we find that the original GCM aerosol climatology has some problems in size specification. The sizes may be too large, and we don't have enough absorption, especially over several key regions. And then our optical depth is biased low overall. And also this sensitivity study here shows that the direct forcing can be very sensitive to changes in these parameters, especially to the adjustment of aerosol size. So based on that, we developed this optimal fitting method to adjust the size assumption in the GCM. Basically, the fitting method reduced aerosol sizes for most species, and then also we adjusted the fraction of absorbing and non-absorbing aerosols. And after that, the absorption is also increased. Then some implications from this study is that so our original aerosol size needs to be decreased for most species. And then for sea salts, as we've seen on that map, we have kind of a bimodal distribution. We have larger values over some northern hemisphere and lower values over southern hemisphere. So we may need a bimodal distribution for sea salts. And then the absorption may need to increase by about a factor of 2. And this factor is actually very similar to the results from Sato and Hansen. And they also adjusted the amount of absorbing aerosols with AERONET, but that's based on global mean value, not station by station or regional basis. So in the future, as mentioned, I will try to incorporate the internal mixing of black carbon with other species. That's like some like Susanna's model or some other studies here already have internal mixing or have some microscopics of aerosols. So those can be very useful in improving the GCM results or only see the differences. Then I also plan to validate the height distribution of aerosols using Calypso data. Because the height of absorbing aerosols is especially important for the direct forcing. And they haven't been really validated, so I'm planning to do that using Calypso LiDAR. And then we have a multimodal distribution of sea salts from ModelE. We haven't used that in the model, so I will also try to incorporate that into the radiation part. Then finally, since we only used AERONET in the fitting, then maybe next I'll use satellite data which has a more complete global coverage in the fitting and compare the results. But satellite data usually are not as good as AERONET, so there may be some differences and also some complications. Okay. So that's all for my talk. Thank you very much.
You showed the AOD, ModelE AOD compared to satellite was pretty close, but Angstrom coefficient showed a large difference. So that means there is like a size assumptions are not good, but your AOD was good enough? And how do you get good AOD with your room size?
Yeah, this is not good enough. It suggests our size is too large compared with the results we get from observation. And then from AOD, because this is 550, and we also have a lower LD, low biasity LD overall. So, so from that relationship, actually, the AOD is kind of inversely related to size. So that means if we decrease the size, then we may get an increase in AOD based on the same mass density. So by adjusting the size, by decreasing the size, we also it also helps to improve the low bias in the AOD.
So when you compare with the AOD after optimal method, like a clearly improved compared to old AOD?
Is like this one. So when we decrease the size, then AOD for like East Asia and also here, these are originally they have been underestimated, now they are become larger here, and not all of them.
So that's purely by the changing size.
That's not purely by changing size, because the relative amount of absorbing aerosol is also adjusted. So for like South America, South Africa, and East Asia, that's where we have lower absorption. Then this increase is also partly due to the increase in absorbing aerosol.
So then do you go back to the transport model and tell it to do the right thing? I mean, because the whole point of a GCM is to predict the future, right? And if all you're doing is tuning to right now, I don't know how that helps to predict the future.
Yeah, right. So right now, because this is current climatology, suggests maybe in the chemical transport part, maybe you have to increase, for example, black carbon by 2 here. So that helps. At least it makes current climatology better compared with observations, and we only have current observations. So those results I think are useful to predict future.
So you give this back to them maybe, and it's their problem. The chemical transport model people. I mean,
because here I concentrate on the radiation part, but obviously the absorption part, with the absorbing optical depth is not purely from radiation. It also depends on the amount of absorbing aerosols you have, and that's in the chemical transport part. And if we get this a factor of 2, it's very likely that we need to increase the mass or total amount of absorbing aerosols by 2 in the chemical transport part.
But I think that I want to ask you that part because when the AOD is maybe overestimated or underestimated, it could be by mass concentration, but it could be also you using the I don't know how can I say you using bad effective index, or because you have to assume that when you're using model. So for the black carbon, there's many studies try to come up with which is a reasonable effective index, but then I don't know. Really, depending on how you choose that number, absorption, especially absorption, AOD is really affected by that. But then, my point is that you have to know why AOD is underestimated. It could be by mass, or it could be by your property, the optical property.
Right, that's true. The optical, the index we're using are actually for black carbon is this one is and that's also from the size table that I showed. We have a larger size. And now, because this is some initial results here, so I will, it's good to compare this new results with other models. It's just for the moment, this result is not that final yet.
It's a little bit the same question as Andy asked. So you see that the sizes are too large, and then you kind of say, okay, what size do I need to get an agreement? And so you find the right size. But you have not yet found an explanation why the size is to be smaller in the GCM. And finding an explanation is important because you'd like to know, if you're making the same mistake for future predictions. My question is, do you know if your correction for the size, how much of that can be attributed to, for instance, uncertainties in hygroscopy or uncertainties in internal versus external mixtures that also affect, I guess, the growth of aerosols? Do you have any idea?
So I know there are lots of complications in this area because it's like we find our tau is biased or absorption tau is biased by this amount. Then there are several factors coming in, like the mass itself, the size, and the hygroscopicity, and internal mixing. So for absorption part, I can have, because we know like including internal mixing may improve absorption by about factor 2. So that may be a very big factor in accounting for that error. And then the others, for relative humidity or hygroscopicity, I have some sense that's more regional. And for some parts, because I compare the relative humidity field, I find that especially over Europe, we have too high relative humidity, and that's mostly causing the low bias in Angstrom exponent and also low bias in tau, because the size become too large. So that may be a main factor there. And for some other regions, I feel the size actually did relatively good job in correcting most of the other regions, and also, most of the other regions not dominated by absorbing aerosols where we can include internal mixing, and not Europe where the relative humidity makes us wrong. Then those places maybe the size can be the major factor there. But still, I can't say for sure what percentage are from size or what percentage are from the other factors.
I have an easy question. So I don't really follow the direct effect stuff very closely, but John Petra, this paper about 10 years ago, looking at subgrid scale variability, such if you use the average humidity versus if you resolved it with a cloud resolving model or something. I think the answer was you get a high bias if you use the average relative humidity. So is that common? Does everyone take into account that bias? No, that's just pretty much ignored. It was a nice paper, but no one does anything about it. Do you know that? I mean, it's a really nice paper.
I don't know the paper, but for aerosols model, we just use like created
the average.
And I just want to add one. I don't know, do you
I recommend everyone doing that. Read that paper and think about using it because it'll bring down your sizes.
Yeah, but I want to comment something that her work is actually good for Dorothy's model, and Dorothy's model doesn't have a microphysics, and the model need to assume the certain size for the aerosol optical depth or something. She need to assume certain size. Unlike some aerosol microphysics model, we start from a size of assumption for emission, but once we assume that, then microphysics take care about the size information. So as time goes by, they might be different. So meaningful for that one. But for Dorothy's, she needs to assume the size, and what her study showing is that her assumption for size wasn't quite right for the AOD or like optical property, so she needs to adjust to make it better or more reasonable.
So it wasn't really a prediction, it was just an assumption in the first place.
Yeah.
But I have a question about that. So for someone, and again, this is totally naive also about how the GCM works, but for the climatology, you can just grab the climatology, right? And you don't actually have to run the, all the aerosol chemistry. Is that true? Like you could use that for some types of runs?
I can tell you about my old, my PhD work. So I was using GCM 2 prime. It's not the ModelE, but older version of GCM, and I didn't perturb any meteorology. I used GCM meteorology and just compute the AOD over time and compare to the satellite. And they look pretty good.
What you were using a climatology?
Yeah, climatology from GCM.
So with Susanna's model, could you still have a climatology like that, or you would never use her model like that?
No, I think you will have the same climatology, just that.
So you might have to still evaluate it though somehow. You still could adjust it. That's because that's this exercise, right? That's trying to get something in line with with AERONET.
Actually, perhaps I'm not a very good person to tell that. Perhaps Andy could answer, but GCM has their own AOD or some AOD for the climatology.
Yeah.
Sometimes we override it for certain study, but sometimes we don't override because that already gives a reasonable, climatology.
But even the climatologies for the GCM, they usually come from a model, right? Because you cannot
No. I mean, aerosol model and there's a radiation model. Many times radiation model has their own aerosol to compute the AOD.
But where does this come from?
That's what Andy does.
Yeah, but I mean, it's a three-dimensional field, right?
Well, it comes from Dorothy's model, basically.
Exactly. That's what I mean. It still comes from a model. It's not because observations cannot give you three-dimensional.
And then you take the model and you try to adjust it to make it match observations, surface observations after the fact. In this case, assuming that the masses are right and that your only problems are in size. Is that right? But I'm wondering if you could actually end up in a situation where you would need to do that with Susanna's model too, for the same reasons. To produce a climatology with Susanna's model, for instance, for indirect effects or something, where you wanted to actually use her models, her aerosol model. But I don't know if that ever arises, so I was just curious. I don't know. Anyway.
I think the aerosol has compared to cloud or other, climate agent, aerosol has a small impact on climatology. So perhaps that the small error doesn't make a big problem eventually, but
I understand what you mean. If that model, it depends on how that aerosol model is parameterized. Because eventually, I think it also needs to convert the mass into optical properties, and that what radiation model is doing. We specify its size and its refractive indices, and then also hygroscopicity, and then convert this mass into optical properties.
And I guess she has a lot of mixing state too.
Yeah, that's I don't I haven't worked with any mixing models, so I don't know how their aerosols are specified or how their mass are calculated in the first place. So it's probably we can use similar exercise on their aerosol field if we get the mass, and we assume some kind of different refractive indexes. For this mixing state, then maybe we can still try to adjust them the size specification using that.
So you assume totally externally mixed?
No, here is totally externally mixed.
So that alone, going towards a mixing state would really increase your absorption, wouldn't it?
for the black carbon, yes, but not for others.
Right. So, but that could really be a source of some of the absorption problem. That's kind of a limiting case.
Yeah.
A low, absolute lowest absorption. I just have, we're future for this, I mean, this aerosol model for kind of very long GCM runs or stuff like that, that you would use, I mean, I guess this is a current day climatology, so.
For the long.
Do you expect people to use this climatology, this improved climatology, and if so, for what types of runs? I mean, I guess.
I myself have looked at some forcing differences using this new climatology, and so for one reason I'm not using microphysics is now I think it's still very slow.
Yeah.
It doesn't give you if you only care about the forcing, then that's too slow to use for that.
And I guess the other problem is you have to accurately predict some things that are actually sometimes easier to specify. If you don't do a good job of predicting them, we encounter that in cloud physics too. So, okay.
Yeah, and here, although I said this is not like anything final, but for one thing, it suggests some direction for future improvement. Because if we only like we increase some mass of absorbing aerosols, we can get a good agreement with observation, and also the model is still running very fast. But this doesn't involve microphysics, so it's very fast. Then also when we have better data, like because AERONET currently is the best data I can use. I compare satellite data with AERONET and see some differences, especially in the Angstrom exponent, and also retrievals need to assume the size and other assumptions. So currently the data are not very good. But if we have better data in the future, then this may give a more like complete result. So I believe it can be used to look at forcings or calculate forcings better.